So afternoon, everyone. Let me first thank you all for being here. Really do appreciate it. And I hope you get the most out of the presentation today. So without further ado, let me introduce you to our team. We are Arsani Sinout, Lamine, Omar Helmy, Salma Talaat, Youssef Sheta, myself, Mohammed Samir. And of course, we all under great supervision of our all-time favorite mentor, Dr. Amr Goneid. So before we start, let me walk you through our presentation's timeline. Next slide. All right. So we'll be starting with the objectives and problem statement, where we are going to remind you of what are we exactly doing and what are we trying to solve. And then we move on to the methodology, where we're going through all the stages we need to conduct in order to reach our final results. And again, a data specification, where we introduce you to our data set and all the preparations we had to take in order to get them ready to use. And then finally, experiments done so far, which actually took most of our time for these two, as we were eager to come up with the best and most accurate final results possible. So now let me leave the floor to my friend and colleague Lamine to talk about our problem statement.
So our main research emphasized throughout the past two semesters emphasized on investigating the robustness of our methodology in the recognition of ancient Egyptian artifacts using shape features and content-based image retrieval. And throughout thesis 1 and 2, what we're trying to solve, we were intrigued by the CBR technology or content-based image retrieval. So we looked up on the most efficient CBR methodology to recognize ancient Egyptian artifacts.
Okay, so as a start and to put you like in the frame of our work in our last two semesters, here's a snippet of the outcome and what could be translated into an application that recognizes Egyptian artifacts and gives details about them. And my colleagues will elaborate more on the research aspects of the problem. And these are some examples of the images that we are using and them after they are recognized. So in the simulation, we take a picture of an artifact. Then it's going to be recognized by our data set after taking a certain specimen. Then the artifact found will provide us with the information about the artifact itself.
So to dig deep into our detailed methodology, it consists of three main stages as shown, and which we go through in details with. First, we read in the image, then removing all the background noise from it. Then we stretch the image and adjust it for the process afterwards, as you can see from left to right. And following that, an image is binarized to reduce information contained within the image itself. And this will help us compute the threshold that differentiate the object from the background. And finally, we complement the image to calculate the distance transform, which will be negated afterwards to be used by the watershed method that will be explained by my colleague Omar.
So in order to explain the segmentation, the aim of segmentation is to simplify or change the representation of the image into an element that can be easier to analyze and locate the object. That's why we introduced the watershed segmentation algorithm in artifacts recognition. Watershed is a transformation defined on a grayscale image. It's an algorithm used for a segmentation process, as it is also used for separating different objects in an image. In order to explain watershed process and segmenting objects, it fills the object with water to perform the watershed segmentation. It provides a useful complementary approach to the segmentation of objects, as it can be used for segmenting objects that are touching each other. The watershed function takes the image as an input and stores it in a labeled matrix image. So we used watershed segmentation of objects as it changes the image into another image, as we can see in the two images in front of us, by using basic transformations whose catchment areas are the objects we want to identify. We computed the distance transform of the image's complement, then the distance transform is negated to convert the bright areas in the image into catchment areas, which is our aim to perform feature extraction afterwards. Feature plays a very important role in the area of image processing, Before getting features, various images, pre-processing techniques like binarization and thresholding, like my colleague Lamine said, are applied on the sampled image. After that, feature extraction techniques are applied to get features that will be useful in classification and recognition of objects. The main goal of feature extraction is to obtain the most relevant information from the original data and represent the data in a simpler way. We chose feature points extraction since Egyptian monuments have similar boundaries, which would make confusions if we used boundary extraction. Therefore, we decided to use feature points extraction. So for fast feature extraction, we used the feature extraction algorithm called fast feature extraction, detects feature points of the object and marks them based on the watershed segmented image. Then I'll leave the floor to my colleague Samir.
All right, so now that my colleagues explained that we will be extracting feature points based on the watershed image and that we obtained, now let me explain to you what exactly these feature points basically are. A feature point is nothing but a combination of three numbers and digits. The first two numbers are the x and y coordinates to describe position, and then a metric number which describe the strength of each of these feature points. And then when we first started the experimenting, in fact, on our data set, which was relatively small to the one we have now, we were taking up to 200 feature points from each image. Yet this has, in fact, changed dramatically after conducting more and more experiments as we faced a couple of limitations along the way. Next slide. A couple of these limitations were, after enlarging our data set, we found out that some of the images cannot provide actually more than 100 points as they reach saturation after that. And then when we're scaling, another one of the limitation is that when we're scaling our images to smaller sizes, in fact, some of the images even couldn't really come up with more than 20 feature points. And again, so many other limitations will be discussed again further with my colleagues. All right, so now with the Manhattan distance, and we need to calculate the distance using distance matrix algorithms. So after conducting so many experiments in pieces one, we have narrowed down the enormous number of distance metric formulas to only these two in front of us here. Yeah, we rather go with the Manhattan distance as it has actually, due to its less complexity and it's quite faster, but they both still are really great distance measures. All right, next slide. So now talking about the Manhattan distance, we do not only calculate the Manhattan distance, but we also do calculate what is called the maximum Manhattan distance, which we use again in order to calculate the normalized Manhattan distance due to having some images that they possibly could end up having the exact threshold. So how we do this? We start doing this by just comparing the original image that we have to a plain black image that has 0 coordinates, hence 0 points. And then since the black image have 0 coordinates and 0 hence the points, so it will be ending up to help us find out the maximum Manhattan distance for a single image. And then after this, we use all these information to calculate what we call the normalized Manhattan distance, which is nothing but dividing the Manhattan distance of the original image that we had over the maximum Manhattan distance for the same image that we got. And then this will assure us to have the result between 0 and 1. And of course, approaching 0 means the images are, the objects are similar, and approaching 1 means vice versa. That is, the objects or the images are not really similar. And Omar will continue with you on this.
So in order to test our feature extraction algorithm, we performed 3 cases. In the first case, where we applied the similarity distance on identical images, the result was 0, as there was no difference since same feature points were chosen. In the second case, where we applied the similarity distance on different orientation of the same object, the difference in the output for Manhattan and Euclidean distances are considered small, as the Manhattan distance calculated is very close to 0. The third case is considered more distant compared to the second case, which means that similarity is reduced compared to the second case done previously, which can be clearly seen in the difference between the normalized Manhattan distances, where the second case for the normalized Manhattan distance is 1.4%, and the third case for the normalized Manhattan distance 0.6%. We introduced the watershed segmentation process in addition to the selection of the strongest feature points using fast algorithm to serve our aim in recognizing the artifacts accurately. Then I'll move to our colleague Salma.
We took the images of our data set from the Egyptian Museum. This museum has over 160,000 artifacts, and they date from the Naqada III period, which in Arabic is called Asr Maqabr al-Usrat. And it's from 3200 BC to 3000 BC. We managed to take pictures from the Egyptian Museum after a lot of hassle. We had to contact several people to get the approval, especially during the pandemic that we are going through. It took us several trips to the museum in order for us to build the data set. We have over 250 pictures in our data set. Out of the 160,000 artifacts, over 50,000 were transferred to the National Museum of Civilization, which is still under construction. Therefore, in our data set, 5 pictures were extracted from a public source. Even though our plan was to have all of the pictures taken from us, and due to the displacement of the artifacts, most of the monuments in the Egyptian Museum were unlabeled. And therefore, we decided to categorize them into different classes as mentioned in the next slide. The classes that we chose are as following: the headrest, horse's eye, faces, miniature coffins, palettes, pottery, sandals, seated statuettes, tablets, wooden statuettes, canoptic jars, statuettes from the Karnak, wooden limbs, and finally, Nefertiti. Moving on, in order for us to build our data set, we had to go through different phases. The first phase is, of course, taking the pictures, and here are 2 examples of the pictures that we took. Then, for the next phase, we remove the background of the pictures as seen in this slide, in order to have a clean data set where each picture contains only the monument and no other object in the background. To remove the background of the pictures, we used an online software which caused us a small challenge that we can see in the next slide. For many pictures, the software failed to completely clean and remove the background, and it is crucial for us to have clean pictures in our data set, since when we have some unclarities in the picture, they may cause detection of those unclarities as seen in the next slide, rather than the detection of the features of the artifact itself. To overcome this challenge, we had to remove the unclarities manually, as seen in the next slide. However, removing the unclarities manually can cause either overcropping in the picture on the left, or creating some sort of a border around the picture, as seen in the picture on the right. Moving on, Arsani will talk us through the tests we ran.
I'm sorry, I was muted. Okay, using our collected dataset and our proposed methodologies, we will now show you a live demo of our work based on certain attributes that we explored throughout the testing that will be presented later in this presentation. As we can see, the inputs to be inputted are the image number, which we could like enter 61, and we have to enter the variance of the image because one variance or one angle, so one. And the image is recognized, as we can see from figures 1 and 2. The same image was recognized, and a brief about the image is shown in the English and the Arabic languages. So this is not our mainly field of concentration. We are concentrating more about exploring the methodologies and the attributes that will lead to what we saw in the live demo. So now we'll talk about the testing and how we managed to use images of the data set along with the methodology we attained to get useful data and test the efficiency. In our testing phase, we tested the effect of the following on the recognition rate: the number of feature points, the strongest number of them, the threshold of the similarity distance, which is the Manhattan distance, the orientation, as in the angle of the images, the size of the image as its scale relative to the original size, and with relative to the size, we test the average execution time of the image. So in our testing phase, we define recognition and measure it by two statistical rates. First, the recognition rate, which is the rate in which an image is recognized correctly, and second, the rejection rate, in which the rate which our methodology fails to recognize an image. Walking through our previous tests briefly to show the development and exploration. For our first test, we use a small set of images to give us a clue or indication of what specific values to test on our huge and final dataset and how to get the most out of our final test. It was 10 images large, each of 500 to 600 pixels of width. We tested from 20 to 200 number of feature points with step 20. The threshold we took from 3% to 12%. As we can observe, the threshold effect affected the recognition rate in the first graph. However, in the second graph shows unsteadiness and clearness of the effect of the number of feature points on the recognition. Basically, that was because of some problems that we with the data we took for this test, as shown here. In the first two examples, images were taken from different angles on the vertical axis, which seemed to negatively affect the recognition process. And as shown in the two samples below, some images had unclear backgrounds, which also affected the recognition of features. So we decided to hold another test to avoid these problems, this time with horizontal angle variation, same range number of feature points, but wider range of threshold points from 1% to 15%. As we can see from the graphs, the need of images with better angle orientation affected the recognition rates positively. As we can observe, the threshold more or less had the same effect, but clearer. However, the number of points graph now shows meaningful data explaining the effect of number of feature points on the recognition process. Okay, so comparing test 1 and test 2, we can realize the difference in angle direction. As we can see, test 1, the angle is vertical direction, however, test 2 is in the horizontal direction. As shown in the graphs, horizontal angles variances shows steadiness in the graph of true positives. Therefore, they are obviously better in our case. Our third test was based on the final test in the previous tests was based on the same test images for test 2 because they gave better results. We scaled images from 0.25 of the original size to double the original size with step of 0.25. As we can see, the recognition rate always gets better when the scale increases. However, they affect the average execution time, as we will show later. Our final test, we used our final data set that contains more than 250 test images with the same size of width of the tests before. However, narrower range of numbers of feature points because when we widened our data set, some images could not give more than 107 feature points. So we took the number to be from 10 to 100 with step 10. However, the threshold widened the range from 1% to 20%. The larger dataset gave us a clearer yet similar idea about the effect of the threshold on the recognition. So as we can see in the threshold, the below two graphs, the threshold on the recognition rate, it increases the recognition rate until it reaches a steadiness point, and the same effect, but in an opposite way, is applied on the rejection rate. The effect of the number of feature points on the recognition is shown in this graph. This graph only shows that our methodology's efficiency having the recognition rate significantly more than the rejection rate, considering the number of feature points. So to dig deeper in the number of feature points effect, we can show these two graphs. The graphs show that the ideal range to use is between 40 and 60. This range of number of feature points shows steadiness both in the graphs of the recognition rate and rejection rate affection by the number of feature points. So in our final test, we also tested the effect of the size. So we used the same data of the previous test. However, we fixed the number of feature points to be 20 and the threshold to be 0.6. Maybe number of feature points 20 is really low, but this was a limitation in our in testing the size, because scaling the image to 0.5 could give fewer number of feature points. So some images could not give more than 23 feature points only. So we had to fix the number to 20 to all the sizes, the scales. For scale 1, scale 2, we had to limit the number of feature points to be 20 in order to have only one variable, and it is the scale with the relation to the recognition rates. So we could see here that some images in scale 2 had few feature points and could have been better if used more number of feature points. So the effect of the size or the scale on recognition, as shown below, basically the recognition rate increases and the rejection rate decreases along with the increase of the scale. So the bigger the image, the more the details, the more the feature, the more the recognition is more stable and fruitful. So as testing the size or the scale effect, we had to study the scale effect on the average execution time. So as we can see, the time varies between 0.35 second to 0.42 seconds in a steady way. However, if we can see that number 1, where scale 1 or the original scale is an outlier with lower timing than, or lower average execution timing than expected. That's because having the image in its original size would not need resizing it. So basically the increase in all the others is the increase of the resize function. So in conclusion, these were our four tests. In our first 2 tests, we studied the effect of number of feature points, the effect of the threshold, and the effect of orientation on the recognition rates and the recognition process. In test 3, we only studied the effect of the image size, and in test 4, which is the final test that we're showing today, we tested the effect of the image size, the threshold, and the number of points on the recognition rates and on the average execution times. So a summary of our contributions and empowerment incomes. As we are having a research, we reached some conclusions about the recognition process, that the axis of image angle is very important because vertical axis deflects the recognition process. The scale basically shows that the larger the image, the more the details, the more the recognition is better. Feature points strongly depend on the scale of the image because as we saw that some limitations were due to the scale, so the feature points were limited. So the threshold is dependent on the number of feature points. So having higher number of feature points would mean having more images into recognition, which means we will need higher threshold. So and it depends also on the saturation point on its graph. The average execution time depends on the scale of the image and the number of feature points chosen in the image. Now we'll move to our colleague Youssef to talk about future work.
Okay, so according to our future work, we will continue on improving the robustness of our methodology, and we will expand and experiment with even a larger data set. And we will draft the research and apply for publication, of course, under the supervision of Dr. Amr Goneid. Next. So we have to give special thanks to Professor Amr Goneid, who was a great member and a very resourceful throughout our research journey, and to the references. And these are our references for the public resources that we used in the images. And thank you everyone for attending our presentation.